two that I want to hit real quick. We're going to talk a little bit about specialist experimental designs and use that as actually as a segue to saying a word or two about basis set analyses and what a basis set is, the analysis of fMRI data. But then most of our time today will be spent talking about taking fMRI data seriously in terms of its spatial extent and making inferences across the entire map of the brain instead of just, so far, our conversation has been limited to single voxels. Okay, so starting digging right into it and talking about specialist experimental design. So yesterday we talked a little bit about, in general, different sorts of experimental designs and how, when you're designing an fMRI experiment and you're planning on analyzing the data, the technique you normally adopt is to start with a model of neuronal activity. Right? You make a little a vector which describes what the neuronal activity would be like in a hypothetical voxel of the brain that responded only to one of your experimental conditions. And you do that for each of your experimental conditions. And then you convolve that with a representation of the hemodynamic response function to get a representation of what you think the bold fMRI signal would be. And then you enter that as a covariate in your general linear model. Right? Is everyone kind of up to speed on that? No questions about that? Okay. And we also talked a little bit yesterday about different kinds of experimental designs and their relative power and randomness. And we contrasted a blocked event-related design, a block design which has maximal power but minimal randomness, in contrast to a variety of what are called event-related or rapid event-related designs that have some degree of randomness at the expense of power. And we finally ended up identifying a couple of intermediate designs, so-called stochastic designs, which allow you to have to sacrifice some randomness for the sake of gaining a fair bit of power. And so we talked about those designs as well. And any final questions about that? I've made reference a couple times, by the way, to a paper by Frank and Liu, which is very approachable. It was in Neuroimage 2004. It comes in two parts. The first part is a mathematical treatise with lots of equations, and the second part is the intuitive part, where they try and take all the information that was provided in the first paper and provide an intuition for its understanding, and then provide specific recommendations for design of fMRI experiments based upon those findings. So I commend that paper to you. Okay, but what about other sorts of experimental designs? Well, there are a couple of other types of experiments you might want to conduct that don't broadly fall within the categories that we've talked about so far. And the one I want to start off first with, have a seat, sir, is what might be called a within-trial discrimination design. And so these are experiments that are designed to identify neural activity which comes at some point intermediate between other 2 points. So why might this be of interest? Well, so when we've talked about randomness and randomized experiments, we've been working with the presumption that the experiment will proceed perfectly reasonably with a perfectly randomized design. So for example, if you're doing a learning experiment, you have someone learn a list of words, and then you subsequently present words later on, some words that are new, some words that are old, and the subject's job is to determine when the word comes up, is it a new word or an old word? They have to perform a recognition task, right? So there, the behavior that you're interested in is actually enhanced or optimized by having there be no predictability as to whether or not the next word is going to be a new word or an old word, right? The subject won't be able to know what the next word is going to be. So you want that total randomization. But how about this kind of design, where what you want to do is study the neural correlates of working memory, which is the ability to hold on to a piece of information across a brief delay. For example, I tell you my telephone number, and you have to recall that information for a few seconds while it takes you time to walk over and punch that number into a telephone. So typically the way that working memory has been studied is by presenting a stimulus, having a brief delay, and then presenting a probe, which requires the subject to make a judgment based upon that information that they had received earlier, right? So a classic example might be, I present the letter A, and then there's a blank screen for a few seconds, and then I present another letter, and then the question is asked, is this the same letter as the one that was presented before? Okay, that's a pretty fairly trivially easy experiment, but you can imagine a lot of other versions of it where you have to remember spatial information. For example, a couple dots come up in particular locations on the screen, then there's a delay, and then subsequently a circle comes up, and your job is to determine, is this circle around one of the positions that was previously denoted by a dot, right? So this is a working memory type experiment. So you might say that, well, the different sort of states that the subject is in during the course of this experiment is the presentation of a stimulus, there's a delay, and then there's a probe or a response period. Okay? And in a lot of cases, at least for a long time within this field, and I should say that the world of neuroimaging was just swept up in working memory studies for the better part of 5 or 6 years. but the great interest was being directed towards the delay period. So what's going on during the delay period? Is neural activity increased, for example, in prefrontal cortex as a marker of holding this information across the delay? Well, thinking about this in terms of our randomized experimental designs, if we treated stimulus as one condition, delay as another condition, and probe or response as yet a third condition, and then tried to randomize those, we'd obviously do fundamental harm to the notion of working memory, right? So if the experiment was, stimulus, stimulus, delay, 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 probe, 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 delay, stimulus, delay, right? It wouldn't have any meaning, right? Delay only has its meaning as a psychological construct if it falls in between a stimulus and a probe, period, okay? So obviously we couldn't use an event-related design where we perfectly randomize these events. This is a unit that must remain as an intact whole for us to study it, okay? Yet nonetheless, we still want to try and identify neural activity associated with just this delay period. So the technique that one can adopt is to try and model neural activity during each component of this trial and trying to resolve them separately. And so the way that's probably the easiest way to think about it is imagine a neuron then which had neural activity just during the stimulus period, and it would have a response that looks like that. And another neuron which has neural activity just during the delay period. Imagine it looks like that. And another neuron which has neural activity just during the response period. It just looks like that. And if you were to then convolve each of these with a hemodynamic response function, these would then serve to model the pattern of neural activity that might occur during this time. So if you saw bold fMRI data that looked like this, your judgment might be that there was a stimulus response, right? So that when the stimulus came on, there was a neuronal response, that neuronal activity was maintained at above a baseline level during the delay period, and that finally there was another evoked response when the probe stimulus came up. Is that sort of a perfectly clear intuition for most people, just seeing that? Okay, well, the challenge becomes, of course, that you might want to start to move these things closer together, and it turns out the closer together in time the stimulus and the response are, the harder it will be to distinguish these different elements, right, just as a consequence of the sluggish nature of the hemodynamic response function. And just to give you some practical notion of how far apart these things can be and still make it all work, if you have a stimulus at time 0 and a response at 8 seconds, then you can model a delay period and ask, was there neural activity at that period 4 seconds into the experiment? Okay? So that typically is practically about the closest together you can resolve these elements. You could start to move them a little bit closer together in time, but the closer together you move them, your resolving power for these different elements drops off dramatically. Has anyone here either pondered or tried to conduct one of these delay-related experiments? Yeah. So do you have any questions about it or anything further you want to explore in its design? So this is generally the way it's done. And in fact, you can imagine that you might have different sorts of trials. Imagine you have you want to compare working memory for spatial locations versus working memory for words or letters. Okay, so you'd have some trials where you present a spatial location, that there's a delay, and you make a response, and other trials where you present a letter, there's a delay, and then you have to make a response based on what letter appeared. And you might want to contrast the neural activity during the delay period when you're holding on to information about letters versus when you're holding on to information about spatial locations. And so what you just simply do there is you'd say, well, I have two sorts of trials overall. I have the spatial working memory trials, and I have the letter working memory trials, and I'm just going to now randomly assort those. Okay, so each trial, the subject would be unsure whether or not the next trial was going to be a letter or a spatial location, but within the trial, it would have this fixed structure, and then you'd be able to tease apart each component within the structure. Okay. All right, so that's sort of the concept of a within-trial discrimination. But one feature of this that I want to highlight is that the covariates which are modeling the events within this trial have a particular kind of property, which is a nice segue into talking about something called a basis set. So let's take a look at that. So one way of constructing the covariates that appear here is you have one covariate that appears like this. That's the hemodynamic response function to the stimulus. One covariate that looks like this. That's the hemodynamic response function to the delay. And finally, that's the response to the response, the hemodynamic response to the response, or the probe. Okay? And you can imagine that these three covariates can scale up or down, right, to fit whatever particular pattern of response is actually observed. Okay? So the neural activity for one voxel, perhaps in just the motor cortex, right, might look like this. Right? So there's a voxel that's only responding at the time that the subject makes a response. Or there might be a voxel which is located within primary visual cortex, right, which might have this kind of appearance, right? So it just has neurons that fire just during the stimulus and just during the probe, right? Or you might have voxels which have a far more complicated and interesting kind of pattern. You know, who knows, something like this. Right, so what's that thing? Well, you know, what would happen is these three covariates would kind of scale up or down to fit this as best as it possibly could. And we probably have one that kind of actually wouldn't even come up all the way. It would probably come like that, and then the next one would sort of fit just roughly like that, and then the third one would fit roughly like that. Okay? So you'd have an amount of scaling that would be applied to each one. So in a sense, actually, these three covariates would try to model this evoked trial as best as it possibly could. Okay? And by having different combinations of the weighting on the different covariates, you do the best job you possibly could modeling that trial. Okay? In that sense, these three covariates are serving as what's called a limited basis set, or I should say a partial basis set. So what's a basis set? So a basis set is a set of covariates or set of vectors which can be used to model any pattern of responses that might appear in some other vector. Okay? This turns out to be a rather useful concept in bold fMRI experimental design under those circumstances where you want to try and detect an effect, but you're not quite sure what shape the effect will have. Okay? So in this case, we're not quite sure what shape the evoked response in this working memory trial will have. It might be, you know, high in the middle and low at both ends, or, you know, high and then medium and then low. We're not really quite sure at all. So these three covariates can model whatever particular pattern of response ensues. But it turns out you can generalize the concept of a basis set to be even more flexible than that. So imagine we have an experiment where we have one stimulus that's presented every 16 seconds, say a flash of light. And now what I'm interested in doing is finding out what is the shape of the hemodynamic response that follows the flash of light. Okay? Now, so far we've been mostly interested in experiments which are trying to detect changes in neuronal activity and making some statements about the magnitude of the change in neuronal activity. But there are some sorts of conditions, some sorts of experiments where you might be interested in the shape of the response, okay, or comparing the shape of response between one condition and the next. Suppose, for example, you have the notion that stimulus A and stimulus B evoke different patterns of neuronal response. Not necessarily that one evokes more neural activity, but different patterns of neural activity over, say, a 5-second period. Maybe it's the case that stimulus A evokes a pattern of neuronal activity that looks like this, and stimulus B evokes a pattern of neuronal activity that looks like this, where the total integrated neuronal activity in both cases is the same, but they have different profiles. Okay? So you're not interested in answering a question about the amplitude of neuronal response, but now something about its profile or shape. Okay? So one way of being able to address a question like that is you say, all right, well, imagine I have a stimulus that appears in this prototypical example every 16 seconds. This is an example of a sparse event-related design experiment, right? One stimulus every 16 seconds. And I want to find out what is the shape of the hemodynamic response that follows each of these presentations. Okay? And so I've been drawing for you guys kind of what the shape of a typical hemodynamic response function is. But imagine you don't know that a priori. For example, suppose you're doing an experiment in kids. Okay? And so children appear to have different shapes and different relationships of neurovascular coupling from adults, particularly under conditions of anesthesia. So when you anesthetize a kid, neurovascular coupling changes a fair bit from what you see in adults. So this might actually be a relevant kind of thing to take a look at. And certainly I've been doing studies involving dogs, and they have a very different kind of hemodynamic response function from awake, behaving college students. There are also similarities in many ways. So anyway, but you have a stimulus every 16 seconds. And so imagine that there is some bold fMRI data that you obtain from this, right, which looks something like this. Put some noise onto this, a little bit like this, and some of this. Okay. So just looking at this, you guys can start to see that what I've drawn is some data which has a hemodynamic response which has something like this as its property. Okay, at least that was the shape that I was trying to introduce in that signal plus some noise. Okay, and this is different in many ways from what a more typical hemodynamic response might look like, or at least what we've been drawing as our typical response, which has something like that as a shape. Okay. So if I were to try and analyze this data in the traditional manner of make a covariate, and I say, here are my events that occurred in time. Now I'm going to convolve this with a typical hemodynamic response function, the standard hemodynamic response function that I've obtained from adult human subjects that I've studied in this way. And it looks, something like this. What I'd end up finding is that this is a fairly poor model of this data. Okay? This assumed shape of hemodynamic response is a fairly poor model because this is rising while this is still quiet, this is falling while this is still high. I mean, it's going to end up having a fairly poor correlation with the data that I actually obtained. Right? So this would be not such a good model to try and detect that effect. So what else could I do? Well, it turns out that you could create a set of covariates which are flexibly able to model the shape of response that occurred. Okay? And this is the so-called basis set. So what would that look like? Well, you're already familiar with one kind of basis set, which is a Fourier basis set, or the Fourier transform. Okay? And let me show you what that would look like. So imagine that you had a covariate, where again we're going to represent, sort of here are the events of neuronal activity in time. But now, following each event, instead of having a hemodynamic response function, I'll have different sines and cosines of different frequencies. So this first one will be the first sinusoid. Okay, that's covariate number 1. Covariate number 2 will be the second sinusoid. And so on and so forth. 3, 4, 5, etc. Until you finally get down to this last covariate, which is modeling a very high frequency up and down kind of thing. Okay, so now the property of this set of covariates is that if you have them within the general linear model, in the process of minimizing the error, which is, I don't recall if I ever explicitly stated this, but what the general linear model is doing is the way it fits these covariates is it scales them up or down in an attempt to minimize the amount of stuff that ends up in that error term, the E term. So by scaling these up or down, you'll have some fit between this set of sines and cosines and this data, such that the modeled one, so if you take, so imagine this one gets a weighting of, that's 3 units. This gets a weighting of 2.2 units. This gets a weighting of negative 0.7 units. And this gets a weighting of 0.2 units. Okay? So you multiply this one by 3, this one by 2.2, this one by 0.7, this one by 0.2. Add them all up. You'll get something that looks like this. Okay? It will be an average response that fits the mean response across all these trials perfectly. Okay? It'll actually perfectly fit this mean response across all the group of trials. Okay? And the way that you would evaluate this group of covariates is with an F-test. Okay, so now we're used to evaluating a single covariate by taking a look at its beta value versus the error term, and that gives you a t statistic. But when you have a group of covariates like this, and you want to know, do this group of covariates together explain more variance than they would otherwise under just random chance, then you use an F statistic to evaluate that. Okay, so now I've given sort of a broad and perhaps not very intuitive overview, so let's pause here for some questions. Yeah?
Aren't you doing a Fourier transform?
It's in effect a Fourier transform. So this is a Fourier basis set. This is a set of sines and cosines which basically are fitting this data in Fourier space. Now that's one way of thinking about it, but let me show you just to help with intuition in the audience, let me present a different sort of basis set, which is algebraically equivalent, has the same properties, but might be a little bit more intuitive. Here's this basis set. It looks like this. So what you can see is that each covariate is the same as the one above it, with just spikes that are shifted over in time. Okay? And so what would happen then is that this covariate is modeling the mean level of signal at the first point in time after the stimulus, which would be here. Okay? And this covariate is modeling this point in time. And so on and so forth. Okay? So this covariate will get scaled up or down to fit the mean level of signal that's occurring at this point in time right after the stimulus. And this second covariate will be scaled up or down to fit this one. Okay? So what you can imagine then is that this data is being fit by a group of little impulse spikes that look like that. Okay? Each one getting scaled up or down to fit this mean effect. This is referred to as an impulse basis set. Okay, a group of impulses of discrete delta functions which are being scaled up or down to fit this mean effect. Okay? And again, you would evaluate this group of covariates together using an F statistic to assess their significance. Okay? So what's happened here? Well, by looking at the magnitude of the F statistic, we'd be able to find points in the brain where this group of covariates found something, okay, identified some kind of consistent pattern. Even though we couldn't say what the shape was, we'd be able to say it was the same shape every time, roughly, after a stimulus was presented. Okay? It could have been any kind of shape, but at least it was a consistent shape. It was the same kind of evoked response every time a stimulus was presented. Okay? And so this flexible system found that consistent response. And so we can identify points in the brain where that consistent response was found. Okay? We can't, at this point, make any statement about what its shape was, whether it was positive or negative going, what it looked like. All we can say was something consistent that occurred every time a stimulus was presented. So if you start taking a look at the data across the entire brain and the way that looks from an analysis like this, you'd have an entire map of the brain. And suppose what happened was I presented a picture, or I presented a flash of light every 16 seconds, and the subject made a button press in response to the flash of light. And I might end up finding that here's an area of the brain with very highly significant F statistic values, and here's another area of the brain with significant F statistic values. And if I plot out the evoked response from these two locations, kind of the average response across all these trials, what I'd find is that this area of the brain has, this thing, and this area of the brain has this thing. Imagine. Who knows why? There's different neurovascular coupling in these two locations. But at least this was a consistent response at these two different locations. Okay? And in fact, this is the method that was used initially to find out what the shape of the hemodynamic response function was in human subjects. Okay? Because you'd take subjects and you'd put them in the scanner, you'd have them press a button in every 16 seconds, and then you'd identify areas of the brain that had a consistent response without making any assumptions about what the shape of the response was. Okay? So this is a full basis set. It's able to model any possible shape of response that occurs in the period of time that follows the presentation of a stimulus. Okay? So this is the method. So even if you don't understand every last detail, know that there's a method out there using a basis set which allows you to be able to identify responses that you're not able to fully predict their shape in advance. Any more questions? Yes?
In general, how many covariates go into the model?
It's great. How many components, how many of these covariates do you need to have a full basis set? That's great. So if there are 8, say, values in this period of time, so imagine 1, 2, 3, 4, 5, 6, 7, 8. So imagine that this was a 16-second, every 16 seconds I presented a stimulus, and you were collecting data at a TR of 2. So every 2 seconds you got a picture. That means there's 8 pictures of the brain, or 8 time points for each trial. Okay? So it turns out that you'll need then 8 covariates to fully model that. So you need 1 covariate for each point in time that you're trying to model. But it's not 8 times the number of trials. It's just 8. Okay? So 8 covariates model, this trial and this trial and this trial and that trial. Okay, it models all the trials together. Okay, so in general, the number of covariates you need is equivalent to the number of points in time, or the number of observations that you're attempting to model. And one way you can intuit that is with this impulse basis set that I described here, you can see that I would need 1 covariate to model the first point in time, 1 covariate to model the second point in time, yada, 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 the 8th covariate to model the 8th point in time. 1 covariate for each point in time. Yeah?
Is that then also equivalent to the number of covariates you would need in the sinusoidal model?
That's right. So in a Fourier basis set model, you would basically need 4 harmonics, with each harmonic having a sine and a cosine. And that would be sort of algebraically equivalent. But, this might be a little bit easier for folks to understand. Yeah?
A little bit confused on the logic. So you have this function, which is output, after you've done the experiment.
Right.
And you're trying to find an area that is, whatever its shape is, it's locked in time with your stimulant.
Correct.
So you have to find that function, but then you have to find out which areas of the brain are reliably acting that way. So it's a little chicken and egg problem on that.
Well, okay, let's see. So just taking 1 voxel at a time. So you have 1 voxel, and you want to ask the question, did my stimulus produce some kind of consistent response. Did my stimulus produce a response in this voxel? Okay? And so the way you do that is you say, okay, well, here's my data from that one voxel. Here's a basis set. Okay? What was the F statistic associated with that set of covariates? Okay? And it came out to be an F value of 2.3. Okay? And you look it up in the table. F value of 2.3 with the number of degrees of freedom you have is equivalent to a P of 0.02. So you say, okay, so there was a significant response in this voxel to my task. Okay, now you can say, well, how about the next voxel? How did that turn out? Well, that had an F value of 1.3. This one had an F value of 7.6, and so on and so forth. And then just in the way that we would analyze other sorts of data, we'd say, well, okay, now let's correct for the number of comparisons that we've done across the entire brain. Only show me those voxels that have an F value greater than 5. Okay, make everything else dark, and then color these red. So now I've found those areas that had a map-wise significant effect of my task, even though I wasn't able to specify a priori what the shape of that effect was going to be. Okay. So now a full basis set like this, if you're not fully wrapping your head around it, don't worry about it, because it doesn't turn out to be something that you come across all that often. So it's not very often that you would have reason to want to use a full basis set like this. But even if you don't have it all, let me just tell you that there's something called a limited or partial basis set, which you will run into a little bit more often. And so let me try and show you what that looks like. So a full basis set has the property of being able to model any possible shape of response that might possibly ensue following the presentation of your stimulus, right? So that could lead to entirely non-physiologic responses, like this, right? I mean, that is your hemodynamic response function, which seems fairly unlikely from a physiologic standpoint. There's such a dramatic and rapid change, and it just doesn't look like something that would ever physiologically ensue. It might be the case that we'd say, well, look, let's be flexible, but not too flexible. Let's detect some patterns of responses that might occur in a voxel, but not sort of wacky, crazy responses. In fact, let's just detect that family or class of responses which have the property of being sort of smooth, right? So we know that whatever hemodynamic response function is, it's going to have to be fairly smooth. It can't be kind of too jerky and rapid like that. And so it's possible to create basis sets which are capable of modeling smooth functions or responses, but not all functions or responses, okay? And the fewer elements that you have in your basis set, the more efficient it will be, the more powerful it will be. Okay? So if you can effectively model all the stuff that could possibly occur in here with just 3 covariates as opposed to 8, then you have more statistical power, because it turns out your F values are more significant if you use fewer elements like that. So what are some things that you could use to try and model this shape or family of possible responses? Well, here's something which gets commonly used in VoxBo and in SPM as well, for those of you who use that. And that's what's called the Taylor expansion of the hemodynamic response function. All right? And in fact, what this really amounts to is just the hemodynamic response function and derivatives thereof, okay? Temporal derivatives thereof. So if this is the typical hemodynamic response function, which you measure from across subjects, right? You can take what's the first derivative of this thing, which is that dd? I think it's like that. And then, so the first derivative of this, I'm terrible at drawing derivatives. I think it's something, I don't know, like that. So you have the first derivative of this function, okay? First derivative in time. And then you can imagine taking further second and third and fourth derivatives and all the rest. So here's an interesting property of smooth, continuously differentiable functions like this, is that if you have these two things entered as covariates in a statistical model, okay, the hemodynamic response function and its first derivative, these covariates have the following properties. This covariate is going to model the amplitude of the evoked response, presuming it's something roughly close to a hemodynamic response-shaped thing. Okay? So imagine that the actual response, the actual data you observe, is a response that looks like this. Okay? This first covariate is going to do a pretty good job of scaling up or down and fitting that amplitude. Right? That's fair enough. You can kind of just see that visually. What's the property of the second covariate? Well, this is kind of cool. This second covariate actually has the effect of being able to shift this first covariate back and forth in time to better fit this. Okay? The more loading you have on this second covariate, the more this first covariate kind of can get shifted over in time to fit the response. Okay? So if you have, let's see, so if you have this as your data, okay? So in red I've drawn the data now. So obviously this black covariate will be scaled up or down to best as it possibly can fit this red curve, though it's not going to do perfectly because the red curve is shifted over in time from the black curve. If you start to add more and more variance or put more and more loading on this second derivative covariate and add it to this first one, the end result is a model fit which is shifted over in time to fit this shifted version. Okay? So now, you're just going to have to take my word for it. All right? Because unless you really want to go and read a little bit about the Taylor expansion and learn about why continuously differentiable functions have this property, you're just going to have to take my word for it. But it is nonetheless something which is demonstrable and is used to great effect in the analysis of a lot of data. So that's why in a lot of event-related fMRI experimental designs, okay, you have a hemodynamic response function, and then you also include the first derivative of that covariate as well. And that first derivative of that covariate has this property of modeling temporal shifts of the response in time. Okay? Now, anyone who actually with a mathematical background either wants to correct me or illuminate the audience, I welcome. But I just know the terminology, not the math behind it. Yeah, did you have a question?
Yeah, well, the weights of the coefficients of the covariates from the picture before, the number that you get, the
Yes.
weights are coming from the time course, or
So the weights that you get on each covariate are the fits. So it's the beta value assigned to each covariate as the general linear model attempts to best scale that covariate up or down to fit the data.
so essentially trial and error until it's
It's not really quite trial and error. It's not the model is fit not by an iterative process, but in a single mathematical leap or step. But you can think of it if you want to apply sort of a anthropomorphic interpretation to it. It's like it's kind of scaling it up or down until it finds the best fit. But in reality, the mathematics is just a one fell swoop. Yeah.
Can you use the HRF functions and also on a full basis set to model whatever's left over in the end?
Yeah. So what's being referred to here is sort of a crafty approach, which is where you have the hemodynamic response function, then you have additional covariates, which essentially sop up the rest of the variance, the rest of the systematic variance. And then you treat these other covariates as nuisance covariates and then just interpret the main HRF, and that can be done as well, yeah. So the point is that what you can do is you can include these additional covariates, okay? And remember how we talked about before how the general linear model in general does not make any clear distinction between covariates of interest and covariates of no interest, right? It has no idea what you deem to be a covariate of interest or a covariate of no interest. So it's perfectly legitimate to say, this is the main thing I'm interested in, the amplitude of the neuronal response. And it's possible there's going to be some temporal offset between the way I'm modeling the data and the timing of the response that I observe. And I'm not really very interested in that. So as a consequence, let's just treat this as a covariate of no interest. Any variance which is explained by this covariate, that's great, it's out of the error term, but we're just going to throw it away. Just with a t-test, I'm just going to interpret this thing. Okay? Or you might adopt the stance of saying, I want to flexibly detect any kind of shape of response that might have occurred that's sort of a smooth appearing hemodynamic response function, in which case you'd say, I'm now interested in both of these covariates. Let's evaluate them with an f-test. Okay? So in one condition, in one stance or approach to your model, you take this covariate and further derivatives of it and treat this as nuisance covariates of no interest. They're just modeling sort of differences between your hemodynamic response function and your data you're not interested in. Or you can treat this as something you're very interested in which case you're flexibly modeling the shape of the hemodynamic response function in an attempt to detect those sorts of other shapes. Yeah?
Can you explain this in terms of the degrees of freedom? So originally you said a full basis set would have, say, 8 in the numerator, you have 8 factors.
Right.
And then the bottom would be the number of TRs
Correct.
across an entire subject.
Absolutely right.
Or alternatively across all 16 subjects, I guess.
Well, we'll come to that. We'll come to that in a minute. But actually, you probably would not have an f-test like that across all 16 subjects. You do it within subject.
Okay.
But anyway.
So then here, when we're talking about covariates of interest and no interest,
Right.
It's a GLM. These are all just factors you're putting in the model.
Right.
You would still have. It couldn't be a numerator of 2 to look at just your HRF of interest at the top.
No.
You'd have to include all the covariates, whether they're of interest or no interest, in the model, right?
Well, all the
That test is going to include everything.
So what's being referred to here is that an f-test has 2 degrees of freedom. It has a numerator degrees of freedom, which is equal to the number of covariates that you're evaluating simultaneously, and a denominator degrees of freedom, which is closer to your traditional notion of degrees of freedom. That's like your number of observations minus your total number of covariates in the model. Remember how I told you, like, every time you add a covariate to your general linear model, it costs you 1 degree of freedom? Okay? So it's the same thing here. That in an F statistic, the denominator degrees of freedom is just like a traditional degrees of freedom. It's the total number of observations you have minus the total number of covariates you have. So typically, in a typical fMRI experiment, it'll be like, we have 1,000 observations, and maybe we modeled 25 things with 25 covariates. Okay, so we'd be left with 975 degrees of freedom. Your numerator degrees of freedom is how many of these covariates you want to evaluate simultaneously. Okay? If you want to evaluate just one covariate at a time, then you just have 1 degree of freedom in the numerator. So an F statistic with 1 degree of freedom in the numerator is actually the same thing as a T statistic, just squared. So that's just the same thing as a T statistic. But if you want to take the two of these and now say that I'm going to start looking for flexible things and I'm interested in shape, not amplitude, then all of a sudden you have 2 degrees of freedom in the numerator and you got an F statistic.
But you wouldn't just have 2 because you're looking at all the derivatives of that code.
Well, if you wanted to. Okay, so imagine you wanted to have further derivatives, then you could have up to 8.
So you're saying that you do actually 2 F tests. You do one looking at whatever you're interested in, and then you might do another one to look at the noise, these other.
You could do that if you wanted to.
And then you have to correct, I assume, for having done
Multiple
yes,
comparisons.
above and beyond all the boxes.
Oh boy, this starts to get into a very tricky thing, which is like when you want, suppose you want to control the false positive rate at 0.05. Like, do you want to control the false positive rate at 0.05 for like every experiment you do in your life, or for every experiment that's done at the University of Pennsylvania, or for like at what level do we Bonferroni correct for multiple experiments? And so I leave that up to you. That's not something that can be answered kind of within the domain of neuroimaging statistics. But in any event, yeah. So when you have a set of covariates that have these sorts of properties, that there's one covariate that models chiefly the effect you're interested in, which is the amplitude of hemodynamic response function, okay, and then derivatives thereof, which can model sort of nuisance variance or systematic differences between your assumed hemodynamic response function and the actual hemodynamic response function, then you can evaluate these set of covariates in different ways. You can say, just show me the first covariate, in which case I'm evaluating amplitude, which probably corresponds to the typical sorts of inferences that people usually make using neuroimaging experiments. Or you can start to evaluate this set of covariates together, in which case now you're asking questions about the shape of the hemodynamic response function, which is, in certain specialized circumstances, is a desirable thing to do. Okay. There's one other thing I wanted to mention about that. Oh yeah, so it's worth asking, like, well, how practically useful is this? Like there being, having these additional covariates to model systematic differences in the shape of the HRF from the assumed shape. Well, the reason actually this is a useful thing to do is because it turns out that different subjects have rather different shaped hemodynamic response functions. We never talked much about where the HRF comes from or how you measure it, but just to tell you, so back in 1997, Eric Zarin and I sat down and we measured hemodynamic response functions from 24 or 25 people. Right? So we went out and just measured 25 college and graduate students and measured their HRF from primary visual cortex and primary motor cortex and plotted them, and they looked like this. So, subject 1 had an HRF looked like this, subject 2 had an HRF that looked like that, subject 3 had an HRF that looked like that. And so whatever, they were different shapes, okay? They all had this property of having a rise, a peak somewhere between about 4 to 6 seconds, and a decline, but they had lots of different shapes. We were able to find the average response, and that's actually what's used in VoxBo. And it turns out the shape that we have in VoxBo is very, very similar to the shape that's used in SPM as the average or canonical HRF. And that sort of is reassuring. It tells you that English graduate students have hemodynamic responses and vascular coupling very similar to that of us old Yanks with our diverse, ethnic group that contributed to it. But in any event, so the shape of the HRF was very consistent across these studies. But despite the fact that the average HRF is very similar across continents, the specific shape of the HRF from one person to the next person to the next person is fairly variable, okay? And it turns out, though, that within a person, so not only did we scan 20 people and look at the HRF, we also scanned them on multiple days across months and determined that the shape of the HRF is very stable within a subject, okay? So once you've got a particular shape of your HRF, your neurovascular coupling remains the same over time, but it's different from somebody else's. So what that implies, then, is that it is useful to try and model systematic differences between this canonical or average HRF and that of any one subject that you study, because there are going to be differences, systematic differences between what you assume and what's actually there, and that these additional covariates do a good job of trying to model those systematic differences. Yeah?
So if you were to derive each subject's RF on their own, then does that mean you can skip all this?
Yeah, so it was all the rage for a while, and still is a reasonable thing to do, is to try and actually measure from each subject what their HRF is, and then use that in the analysis of subsequent data, right? So imagine on day one, your subject comes to your lab, you do a scan, and you figure out this is the shape of their HRF, okay? Now on day two, they come back and they do more experiments, the stuff that you're really interested in, and when you go to analyze the data, you use this, their own subject-specific HRF, to analyze their data. It's a perfectly valid thing to do, and I did it for a long time. But then I sat down and started to do some of the analyses, and it turns out that it's, kind of plus minus whether it helps you out, and here's why. First of all, to derive or to measure the shape of the HRF, you have to take some time to do it, right? So suppose you take 10 minutes of scanner time to come up with an accurate measure of the HRF for a subject, okay? Well, that's 10 minutes of scanner time you could have used on your other experiment, the one that you're really interested in. So the question you have to ask is the loss of 10 minutes of scanner time for your real experiment, right, is the price you pay in sensitivity there offset by the increase in sensitivity you get by having a better shaped HRF? And just from sort of looking at this over the years, I kind of came to the conclusion that you don't get that much benefit. And I think that the amount of benefit you get from having a more accurate shape of the HRF doesn't really offset the amount of scanner time that you've lost. Now, that being said, if you're planning on scanning somebody over and over again over a course of a couple of months, and this happens, people do learning experiments and things like this, then at that point maybe the cost of deriving their HRF, or if you have a stable cadre of subjects, like you've identified the 10 subjects who like stay awake in the scanner and press the buttons and do a good job, then you might want to derive their HRF and then use that for their analysis ever after. Yeah?
How stable is the HRF over the different areas of the brain?
Different areas of the brain? Tough question to answer. Tough question to answer. And the reason is because you cannot induce on command neuronal activity of a particular profile and timing in association cortical areas. Hell, you can't even do it that well in primary visual cortex. But at least you can get a little bit closer. The problem is, you want to ask the question, is the HRF in prefrontal cortex the same as the HRF in primary visual cortex? Well, this comes back to the two systems problem, okay? All I can do is I can have people look at pictures and make responses and things like this and hope that it's going to induce a brief transient, a transient intense period of neuronal activity in prefrontal cortex at the time I thought it would. But I don't really have any control over that. So if you see a difference in the shape of the HRF between prefrontal cortex and primary visual cortex, you don't know if that's because the neuronal activity differed in profile between those two locations or if the neurovascular coupling differed between those two locations. That being said as a caveat, I think there is enough evidence to support the idea that there probably is some systematic difference in the shape of the HRF between early primary visual or primary sensory cortical areas and sort of heteromodal association cortical areas. And there is some difference. How big it is very much debated, and people are having a hard time answering this. And people are going to animal models to try and answer this, particularly in monkeys. Yeah, Dan.
Well, that being said, why would you not always use a full basis analysis? And who cares what the shape of the HRF?
So use a full basis set analysis.
Right, and just you're looking for consistency.
Always use an F. The problem is because when you go to, so the question was, why not? Okay, then. So if we know that a basis set will always fully model the response, right? And we know that there are these systematic differences in the shape. Why not just always use a full basis set? The problem is that once you start working with F statistics, you realize that they're actually really limited in the sort of inferences you can make, okay? Typically, when we go into an fMRI experiment, we want to ask the question, do bagels evoke more neural activity than donuts, right? Was there more neuronal firing or more, greater local field potential in neurons for bagels as compared to donuts, okay? And evaluating the amplitude of the hemodynamic response function allows us to readily make that kind of inference because we know that the amplitude of the HRF, the amplitude of that bold-evoked response, is proportional to the amount of neuronal activity that was present there, right? We've got a lot of data that supports this idea, right? And we can even make, beyond just saying more or less, we can even make parametric conclusions. We can say that, well, if the HRF was, 2.3 times higher in condition A than condition B, we know that it was, there was 2.3 times more neuronal activity. And there are sorts of experimental designs that people do which rely very heavily upon that. For example, I say, well, look, I'm going to look at evoked neuronal activity or evoked bold fMRI signal in prefrontal cortex, right, for the number of items held in working memory. Suppose I have them remember 1-letter, 2-letter, 3-letter, or 4-letter, and then I look at the amount of bold fMRI signal and, by implication, neuronal activity present during the delay. So this is bold signal in the PFC, prefrontal cortex. And suppose I find this, right? so that as the number of items in working memory increases, the amount of bold fMRI signal and therefore neuronal activity increases, but then it plateaus after a while. Well, gee, that'd be pretty cool. I mean, then I could start to make some statements about, well, this is how information is stored in working memory, and there's a capacity, and when the capacity is exceeded, it starts to do this, and maybe it even drops as you start to have more items in working memory. People have even found this. So then you can start to make sort of very specific statements. But that's very dependent upon making an interpretation about the amplitude of the response. What can you say with an f-test? I can say that there was a response and that it was consistent. And I can even perhaps say, if I set it up right, I can say it was a different response between one item and two item. But I can't say it was higher or lower, if it was positive or negative. As you guys probably know, a t-statistic is a signed statistic. You can get negative t-statistics and positive t-statistics, right, for a positive effect and a negative effect. F-statistics are only ever positive. There's no such thing as a negative f-test, right, or a negative f-value. You can only ever get positive f-values, which means that you can never interpret a response as being like a positive neuronal response or a negative neuronal response on the basis of an f-statistic. So that's why. It's just limited inferentially. OK, yes?
Your intuition that developing a custom HRF for observers isn't as worth it, that was almost entirely based on scanning students at home, right?
Right. OK, now great. So then here's a further thing. So other studies have been done as, OK, well, let's see. So we found these kinds of things in college students and graduate students. How about old people, right? So let's start scanning old people. And how is that going to change? Old people, of course, defined as like people in their 80s or 90s or many decades older than anybody in the room. OK, so old people. So in any event, it turns out, though, that, and so this was done, and we found that there are differences, not so much in the shape, but in the variability of the response in elderly folks. So it might be the case that in those special populations, in older folks, in patient populations, in neonates, in dogs, in cats, it might be worthwhile at that point to then start generating a population-specific HRF. Okay? But of course, the answer, it still might be the case that, so if you're scanning dogs, if one is scanning dogs, it might be the case that finding out the average dog HRF is good enough, and then you just use that to analyze data from all dogs instead of, So as you can see, it can really vary depending upon the population. But since probably by and large most people in the room are scanning college and graduate age level people, what I've said about the HRF holds. But certainly if you start to move other populations, other considerations apply. Okay? All right. Well,